Thank you for downloading this podcast from The Really Clubby Show on Talk Radio 702 and 567 Cape Talk. For more, please go to 702.co.za or capetalk.co.za. Talk Radio 702 and 567 Cape Talk. The Naked Scientist.
Lots of SMSs coming through about the church leaders, Tuli Madonsela and Hlaudi. I'm going to park them and just read them and share them with you later on. But right now, we are hearing from Chris, our Naked Scientist. Hello, Chris.
Hello.
Wonderful to be with you. Let's start with this. You've just written a really important paper on HIV prevention. Heaven knows South Africa needs the message. Tell us about it.
Well, I haven't written it, but I've written it up. I was reading this paper, which came out this week, and I was very taken with it. Obviously, HIV is probably the worst pandemic that humankind has ever faced. We know that there are tens of millions of people who have died of this. We also know that during the course of just this programme going out, that there will be hundreds of new infections and there will be hundreds of people dying from HIV, and we're still looking for a vaccine. It's been very difficult for scientists to, for various reasons, come up with an effective vaccine to prevent infection. For that reason, people have in the meantime explored other ways to try to prevent people catching HIV. Obviously, because sex is the commonest means of transmission, safe sex remains the number one way to prevent getting the virus. But there have been other things that have been shown to be successful. Obviously, in men, if men are circumcised, they have a very big reduction in the risk of catching HIV, 60 to 80%. It's massive. Also, of course, that means that you can sort of secondarily protect women, because if men don't have it, then it's obviously much harder for them to pass it on to the women. But this means that there's still a problem for ladies, because there's nothing that women can do apart from try to insist that men do something. Well, that might be about to change, because this paper by Charles Dobard, who's at the CDC, the Centers for Disease Prevention and Control in Atlanta, they have come up with a gel which can be applied to the genital area after sex and up to 3 hours after exposure has occurred, and it can prevent infection. Now, previously, people have come up with these sorts of gels, and they've been tested in South Africa in various places, but they were gels which were impregnated with drugs that destroy HIV or block the growth of HIV, but these drugs tended to work very early on in the virus life cycle, which meant that if you didn't get them into the right area before there was any chance of exposure, they weren't going to work. So what this group have done and published in Science Translational Medicine this week is they have made this gel which contains a different anti-HIV drug, an agent called raltegravir, which has been on the market for a few years, but this drug blocks one of the last stages in the replication cycle of HIV, the what we call integration step, where the virus adds its DNA, or a DNA copy of its genetic material, into the host cell DNA. And that happens many hours after infection has first occurred, which means it gives a window of opportunity. So if a person does have a risky exposure, or, for heaven forbid, they're raped or something, then this gel could be applied to the area after that exposure for up to 3 hours, and it seems to be effective. When they've done tests so far in monkeys with the monkey equivalent of HIV, a virus called SHIV, it prevented 80% of the transmission events, and in monkeys that were just given a placebo, a control gel that didn't have the drug in it, 100% of them got infected. So it does appear to be very effective for a period of time, and this really is a game changer potentially if they can make this work in humans.
And just talking about this, I mean, somebody's just SMS'd wanting to know, they've heard of other gels as well. How is this one different from other gels that are used for the genital area for women?
Well, the ones that have been used in the past and tested, those all contain drugs that are called antiretroviral drugs, which target the reverse transcription of the virus. And the commonest agent that they've tested so far is one called tenofovir. And in fact, that was a study done a few years ago in South Africa. And that drug targets the conversion of the virus's own genetic material into what we call a cDNA copy. It copies the genetic material into a form of DNA, which can then be inserted into the cell's own genetic material. And that is one of the earliest things that happens when a virus gets into the cell. So if you come in with a drug that blocks that step after you've been exposed to the virus, the chances are some virus particles will have already done that. So you'll be erecting a roadblock after the traffic has gone down the road, which won't work. Whereas if you come in with the new approach, which is to use this drug, it's like going all the way to the end of the road and setting up your roadblock, and then the traffic comes along and then it gets stopped.
Let's go straight to the lines on 021 446 0567 or 11 883 0702. Let's go to Joseph in Benoni. Hi there, Joseph.
Hello, how are you?
Very well. Your comment on question?
All right. I've got two questions that I've got. The first one is concerning if we're comparing the computer and the mind of a human being. I just wanted to check, would we have a specific size of a human mind as compared to a computer? Because I've been checking that if you need to load, let's say, some DVDs in your computer, you'd require quite a lot of space. But if I try to imagine the videos that I've seen since I was young until to today, and the books that I've read, the audio that I've listened to, it really, really requires a lot of space. So I was just wondering how much space would a human mind be? And the other thing is that I've been wondering, if we're comparing speed of processing that is done by the mind as compared to that one of the computer, which one, how would you rate
which one is more superior? Okay.
Of a mind?
Chris, you got the questions, right?
Hi, Joseph. Great questions, by the way, and thank you. So first of all, the memory capacity. Well, the memory capacity of a human is massive, and it must be measured in gigabytes, but we don't know exactly how many. So I'm going to slightly wimp out on that one, because the way a computer stores data is to put faithful storage. In other words, if you give a computer some data, you need to know absolutely that that data is going to be returned to you unadulterated and in a form which is not going to change over time. Now, the human brain is not like that. The memories that you have of your childhood will be memories with gaps and holes in them, and there'll be blurry bits in them which the brain has decided to throw away in order to preserve the core part of the memory. And it can make up the rest. So you think you have a good memory of something, but actually some of it's going to be invented. And that means that it saves some space that way, but then you don't actually know what you've invented. So some of our memories are not as faithful as we think they are, and that's the difference between a brain and a computer. Now, in terms of the processing power, this is really interesting, and I asked this very question to a guy called Terry Stewart, who's a computer scientist at Waterloo University in Canada last month when I was in Chicago, because he is trying to invent a computer program that will model the human brain. And the reason for this is if you can build a model of how the brain works in a computer, instead of having to do experiments on people, which are costly and they take a lot of time, then you could do the experiments on the computer, you could try to discover new things that way, and then you could go to people, finally, and test whether the thing you've discovered really exists. That's what they're trying to do. And the difference between a human brain and the computer system is that in your computer you've got, let's say you've got a quad-core processor. There are 4 processors in there. They're running ridiculously fast, way faster than your brain. But because there are only 4 of them, all of the instructions have to be fed to them one after the other. One, then the next, then the next. So it's like a giant long conveyor belt of things that have to be done. The human brain, on the other hand, has got 100 billion nerve cells in it, and they're like 100 billion individual processors. So your computer's got at least billions of more of the processors than a standard computer has, than your brain compared to a computer. But those individual processors aren't very good because they make mistakes. And so some of the brain is working out how to avoid making mistakes. So there's not a direct comparison between a human brain and a computer, because a computer has a small number of processors running ridiculously fast. Your brain has a massive number of processors running much more slowly, and they're more error prone. But your brain, because it has hundreds of billions of processors, can do lots of processing in parallel. Lots of things can be done at the same time. It doesn't have to be fed one after the other into the processor. So that makes your brain superior in a different respect. And scientists are now trying to come up with computer chips that work a bit more like nerve cells in the brain. They're a bit more error prone, a bit leakier, they make more mistakes, but because you've got many of them, you can afford to make a few mistakes because you can devote some of them to checking up on the mistakes made by the other ones.
Very interesting. Joseph, thank you very much for those superb questions. Okay, let's go to Peter in Houghton. Thanks for your patience. Good morning.
Good morning. My question has got to do, there's been a lot of hype about taking people to Mars lately. On such a voyage, if there happened to be an X-class solar flare, which happens at least 10 to 12 times a year, the radiation would be intense. Now, I gather all of the space stations are kept at relatively low orbits, 300 kilometers only, precisely because of that reason. And my question is, how would you shield humans in a craft that would be exposed to potentially lethal radiation on such a long trip? Even to the moon, I'm amazed that, there were no flares, because I'm led to believe the astronauts could have fried if there had been a flare in the short trip to the moon. But it's very likely if they go to Mars. So how would they shield them?
You're raising a really important point. And in fact, they got the first real idea as to what the level of exposure might be just generally, because you don't need a flare to get a very heavy dose, it turns out. Because when the Curiosity rover, which is the current rover mission, which is exploring the surface of Mars, it's this car-sized rover which was dropped onto Mars. It took off from America in 2011. It arrived in 2012 and began to explore. The rover has on board a radiation detector. And so the scientists thought it would be interesting to activate that during the journey to Mars, which took 9 months, to see how much radiation exposure the rover was getting just in the sort of journey. Because if a human were to go to Mars, they would take exactly the same trip in exactly the same way and for exactly the same amount of time. So this is a good idea as to how much a human would be exposed not during a solar flare event. And the rover was exposed to a radiation dose equivalent to the entire safe working lifetime radiation dose that NASA allows its astronauts to receive, just in the trip to Mars and back. So therefore, even though we're not sending people there yet, this is a big problem to grapple with. They don't know exactly how they're going to do it yet, because basically we don't want to use up a person's entire safe working radiation dose in one trip. We want to try and come up with a way around that. Radiation protection is bulky and heavy and the very kind of thing you don't want to be blasting off into space, because it takes up so much space and bulk, and it's very, very heavy to lift into space. So instead, people are looking at possibly some kind of magnetic shield. And the idea would be that you would use electricity generated by solar power or some kind of, say, thermoelectric generator or some kind of radioactive cell, and you use that electricity to produce a powerful magnetic field which mimics the magnetic shield around the Earth. You mentioned that space stations are kept in low orbit around the Earth, and therefore they're within the envelope of the Earth's magnetic field, and this protects them. We would want to create some kind of similar magnetic shield around our spacecraft so that we could deflect any particles that come from a solar flare or just general radiation around the craft, and so that it doesn't go into the craft and then into the bodies of the astronauts.
Thank you very much, Peter. Let's go to, is it Jean in Benoni?
Hello.
Hi.
Hi, it's John speaking.
John, welcome.
I have a question, too, about sugar. The first one is that my grandchildren seem to get a sugar rush when they have sugar, and all their friends as well. Whereas in the past, when my children were small, they never had a thing like sugar rush. That's the first question. The second question is that I've noticed that ants no longer go for the sugar bowl. They seem to go for protein only. Is there any particular reason for that?
Wow, I haven't noticed that.
No, I haven't noticed that either. My children definitely succumb to the sugar rush, you're right. I don't know about historically. I don't remember having a sugar rush myself, but maybe that's because I was too distracted at the time from having a sugar rush to make the memory. So I don't know the answer to that one. I think it might just be the way we observe it. So we're programmed to look out for this sort of thing, and then we notice it these days. As far as the ants are concerned, ants love sugar, but they also like protein and other minerals. And actually, ants will go and eat anything. They go and grab any source of food and cart it off back to their nests. There will be times of the year when they want more things which are higher in protein than others, because when they're breeding, they need more protein for the queen to make more eggs and so on. So I strongly suspect it will be partly seasonal, but ants are pretty good at eating anything. There's even, ants love bird poo, because bird poo's got phosphate and things like that in it, which they need to make their DNA. So you don't be surprised if you see ants going off and retrieving bits of bird poo back to their nest.
Okay, Wasim in Benoni. I'm so interested in this answer. Good morning, welcome.
Good morning. Hi, Chris. I would just like to know
Morning.
what makes people left-handed or right-handed. What determines that?
Ah, yeah, very good question, this one. And an age-old question, and the answer is we really don't know. The fact is that 90% of humans are right-handed or right-hand dominant, and this is not a new phenomenon because scientists have done experiments where they've gone and looked at cave paintings. There was a lovely study from Montpellier in France about 15 years ago, and they went and they looked at cave paintings, and obviously when people were painting, one of the things they used to do was to hold their hand up against the wall of their cave, take a blowpipe in their other hand, and then blow paint through the blowpipe to make a pattern of their hand against the cave wall. And if you were to do that, which hand would you hold the blowpipe in? Probably the hand you preferred using, your dominant hand. And so when they look at the cave paintings, they find that you get about 80% of the pictures are of left hands. So they then went to the local school and said to the school children, make some hand paintings on these bits of paper using a blowpipe. And they also got exactly the same ratio of right and left hands on the wall as the cave paintings, proving that people probably had handedness even 30, 40, 50,000 years ago. So it probably goes even further back beyond that. Why do we have this dominance? Well, if you look at the human brain, it's not symmetrical. And specifically, if you look at the left side of the human brain, you see a bulge roughly corresponding to the surface of your brain where your ear is. And that bulge is at the bottom of the motor area on the brain, a region called Broca's area. And it's an area which is concerned with output of speech. And we think that speech is such an important function in the brain that it also goes along with cerebral dominance. So that makes your left brain dominant, and therefore your left brain, because it controls the right side of the body, in some way coordinates so that you get language being paired up with brain dominance, and therefore the side of your brain that is dominant controls the opposite side of your body and therefore makes that side of your body dominant. So left brain, language in the majority of people, right-handed in the majority of people. Why that should be, we don't know. And does this run in families? There does appear to be some kind of weak genetic effect whereby left-handedness runs in families. We don't know what the genes are yet, but scientists are looking into that. But there does appear to be a sort of genetic effect, probably a combination of genes rather than one individual one. The modelling doesn't fit there being one single gene causing left-handedness because generations get jumped in families, which you wouldn't see if it was a single gene. So, brilliant question, but we don't know all the answers yet.
Leanne in Benoni, I think your question is very appropriate for a Friday. Go ahead, please.
It's also very appropriate because St. Paddy's Day is on its way. I want to know why the bubbles in Guinness beer fall as opposed to rise.
Oh, that is a good question. And the reason
Shall we experiment, Chris?
Well, I was just going to say we should crack into a camp. It's a bit early in the morning, Reedy, even for you. The lovely question, Leanne, and the answer to this one is that, on the whole, they don't. So let me explain this. If you look at your glass of Guinness, the bubbles that you're seeing going down are the ones against the glass, right at the surface of the liquid where the liquid meets the glass. What is actually happening is that the majority of the bubbles are going upwards, and they're going upwards in the middle of the glass, and as they rise, they're carrying with them a current of liquid. So they're creating a circulation up the middle of the fluid. It hits the surface of the liquid, and the fluid has to go somewhere. Now, it can't go down because there are more bubbles coming up underneath it, pushing it out of the way. So the fluid flows across from the centre of the glass to the edges where the glass and the liquid meet, and then the liquid falls back down to the bottom of the glass, down the edge, and it carries some bubbles from the froth down with it in the same way as the bubbles carried the liquid up in the middle, and it gives the impression that the liquid is falling in the glass, but if you were to look in the middle you'd see the bubbles going up. So it's like a conveyor system, up in the middle, down around the edge.
All right, shall we go to, there's so many people holding on. Some of you we're not going to be able to speak to, so we'll park and we'll take your details and call you next week. So let's go to Cynthia in Sandringham. Hi there, Cynthia.
Hi, Rudy. Good morning to Dr. Smith. I want to know, they say that old television sets give off radiation which are carcinogenic. Is this so? And if it is so, are the new ones safe?
Hello, Cynthia. The answer is that you do get radiation off old televisions because they use something called a cathode ray tube. The way this works is that you have a filament, a bit like the filament in your electric light bulbs, in the old-fashioned incandescent bulbs, at the back of the screen. And when a filament glows, then electrons are mobilised, electrons are negatively charged particles, and they can be accelerated or pulled away from the filament by a strong electromagnetic field. And so what you do with the television set is you have a very powerful electric field between the filament and the screen. So you make the screen, say, positive, and you make the filament itself very, very negative. And this accelerates the electrons through the inside of the tube, and then they hit the screen. And the energy they have when they hit the screen, they impart to a coating on the screen called a phosphor, and that makes the phosphor glow with a tiny spot of light. And you can have different phosphors that make different colours, and that's how you get different colours on the screen. But when the electrons dump their energy in this way, some of the light actually comes out more powerfully than just visible light, and it can be X-rays. So you will get a low X-ray dose coming off of these cathode ray tubes. And were you to have a sufficiently big dose of X-rays, then this can be ionising, it can damage DNA, and it can therefore produce cancers. The risk is vanishingly small because the dose is extremely low. Modern televisions, which use, for instance, liquid crystal displays, LCD TVs, they are literally using a very bright light source behind the screen, which is of LED origin usually, and it's coming through a crystal which either blanks it out or turns it on. So those do not produce any ionising radiation, and are therefore likely to be safer in that respect.
All right. Thank you very much, Cynthia, for the question. Geez, time flies when you're having fun. Chris, see you next week.
Thanks, Reedy. Thanks, everybody. Great questions.
Thank you. I think so too. Neville and Robert, I'm very sorry. I thought we could squeeze you in, but I promise you next week you'll be the first two callers on. We will podcast our conversation with the Naked Scientist.